Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently based at the Helsinki Institute of Physics over at the University of Helsinki, where I study cosmology. Hey David, great to see you in first, as always. Very nice to see you here and thank you for the Love Burst Award. I really do appreciate all of the awards you all send me. So yeah, I'm a theoretical physicist. I specialise in cosmology. So that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically all of the cool things happening inside the universe. And it's a great topic. I love studying cosmology. I love chatting about the universe. Hey Gregorio, nice to see you. Thank you for joining. Thanks for being here. So yeah, I study all the cool things happening in the universe, and I love chatting to everyone about everything fun inside the universe. So that's why I have this weekly show, Cup of Cosmology, where I get to chat to everyone about all the cool things that I get to work on. This is an interactive stream. The idea here is that you can ask me anything you want. If you want to know about black holes, about dark matter, about space, about time, about gravitational waves, everything you want to know, feel free to ask. If you want to know what it's like being a postdoc, what it was like as a PhD student, anything about the 6 countries I've lived in, this is an Ask Me Anything. You can ask any questions you want. Hey David Howden, great to see you as well. And no more cleaning mishaps. I did have a slight cleaning mishap today. Ended up having an accidental shower while wearing clothes. But we're past that now. We're moving on. It's a good Sunday apart from tiny mishaps. And hey Scott, great to see you as well. And don't worry, you're not late, just 2 minutes, it's fine. Got here eventually, you didn't miss anything, so that's fine. So whichever platform you're watching on, if you're on Twitter, if you're on Twitch, if you're on Haps, if you're on Reddit, if you're on YouTube, it's great to see you, great to have everyone here. Feel free to jump in the conversation at any point, ask away. I know if you're on Twitter, you can interact. Join on one of the other platforms. I think the most stable platform to watch me these days is actually YouTube, because the YouTube stream always works without issues, and any comments you ask on YouTube do come here on Haps as well. Of course, if you come over to Haps, you can also give me awards, which is very nice and helps me maintain this show. So if you want to come over to Haps, you're welcome to do so, but wherever you're watching, welcome. It's great to have you here. You have a question about black holes, Scott? Please ask away. I do not actually have a topic prepared today. So today's one of those days where I'm counting on you all asking lots of questions. If you don't have questions, I'm just going to pick a random topic to ramble about. So if you have a question about black holes, please ask away, because I am absolutely happy to answer any questions you have. Oh, how hot are black holes? That is an excellent question. And hey, David, thanks for checking that Twitch is working as well. So that's a really cool question of how hot are black holes, because there's a question of what do you mean? Do you mean like the center of a black hole, the surface of a black hole? Is it emitting any type of heat? So usually when we talk about how hot something is, it's partly about how much it's interacting with its surroundings, how much it's emitting any radiation that it's letting off. Now, black holes are regions of space-time that are so dense that nothing can escape, not even light. So black holes are regions where there is a huge amount of density together. Not necessarily density, yes. It's a region that nothing can escape. In order to escape a black hole, you would have to be travelling faster than the speed of light in a vacuum, and as far as we know, nothing can travel faster than light in a vacuum. So this means that every black hole has an event horizon around it. The event horizon is kind of the limit of the black hole, and it marks a point of no return. Anything that crosses the event horizon is going to fall into the black hole. Anything that is not yet at the event horizon could still turn away, but once you reach the event horizon, there is no coming back. Hey Abyss, great to see you. Thank you for being here, and happy Sunday to you as well. So then comes the question of how do we measure the temperature of a black hole? Because we can't really hold up a thermometer and plug it into the center to see what the temperature is. But we can actually get an expression for the temperature of the black hole which is directly proportional to the mass of the black hole. But this is only relevant if the black hole is evaporating or decaying via Hawking radiation. So then you can have define the temperature of a black hole, which is related to the amount of radiation it's emitting via Hawking radiation. So I want to clarify here that Hawking radiation is not something that is coming out of the black hole. So Hawking radiation, now we know that in the vacuum of space is a big, huge vacuum, emptiness, but in the vacuum of space, you can actually, hey Ange, great to see you, and hey James, great to see you as well. I'm not going to be unifying theory today. If I come up with a grand unified theory, I promise I will come on Haps and tell you about it. but I'm not there just yet. I'm not working on that either, but no grand unified theories today. Okay, so in the vacuum of space, but I like the confidence, but like, you think I'm going to solve grand unified theories? Thanks. I should get on that at some point. So I'm going to be easily distracted today. So Hawking radiation, that's what I was on. In the vacuum of space, you can actually have particles and antiparticles that create themselves and immediately evaporate. So if matter and antimatter come together, they're going to annihilate and produce radiation. Now, what can happen sometimes is that you can borrow energy from this vacuum of the universe to create two particles, a particle and an antiparticle. These are immediately going to come together and give back the energy that they have borrowed to create themselves. This is happening continuously in space. We have this pair production out of the vacuum that then immediately annihilates. The net effect is nothing really changes, so you don't really notice this. Now it's a fun question. I mentioned just now that nothing can escape the event horizon of a black hole. So what happens if you pair produce a particle and an antiparticle right close to the event horizon of a black hole? Now theoretically, what can happen is that one particle is going to fall in and the other one is going to come out. At this point, if you have one falling in and the other going out, you've basically created particles from nothing. Now at this point they can annihilate, one falls into the black hole, one goes out. Now that we still need to pay back the vacuum for the energy that was borrowed to produce these particles, and it's not given back with the particle annihilation. So what actually happens is the black hole loses a tiny amount of mass to compensate for this escaping particle. Now again, this particle is not escaping from the black hole. It is produced on the event horizon. One falls in, one goes out. This is hypothetical. We have not actually observed Hawking radiation yet, but it's something that we think should happen. So you can pair produce on the event horizon, one goes in, one goes out. And at this point, you can actually define a temperature. Now the temperature is related to the Hawking radiation. Again, it is not related to the black hole itself, but you can define a temperature that is related to this Hawking evaporation, and it will depend on the mass of the black hole. This also then gives you a lifetime, because as the black holes are losing mass to this Hawking evaporation, they are gradually getting smaller and smaller, and they will eventually evaporate or dissipate. We say evaporation, but actually dissipation would be a better word, because it's not turning into gas. It's kind of, we don't know what would happen. But if Hawking radiation is actually a thing that is happening, then black holes are very gradually going to lose mass due to the particles being pair produced and one escaping. And this means that eventually black holes can evaporate or they can decay. Decay, dissipate, evaporate, whichever word you want to use here. People use these interchangeably. So this is cool, because when that happens, we're not really sure what would happen. Especially, we're not really sure what would happen to any information that fell into the black hole, because information cannot be created or destroyed in the universe. Now, information is just our way of saying energy. It's just like any type of energy or knowledge that particles carried when they fall into the black hole. Technically, you can create or destroy information. So what happens to the information that falls into a black hole when the black hole evaporates? We have no idea. I don't know the answer to this question. Nobody knows. But it's pretty cool to think about. This is part of the information paradox about black holes. Not going to go there just yet. Hey, Paul, great to see you. Thanks for being here. Don't worry that you're late. I know some people have issues with the notifications. The topic we are currently discussing is what is the temperature of a black hole, but I don't have a specific topic prepared today. So as I mentioned before, you can ask me anything. I know there have been a couple of questions here that I've ignored so far. I will come back to these questions very quickly. Now, if you have a black hole that can evaporate, we don't know what's going to happen to the information, but what is expected to happen is that there will basically be a burst of light. In some frequency, there's going to be a burst of light, and this could produce a gamma ray burst. So then a gamma ray burst is just a burst of highly energetic particles of light, which are photons. So a gamma ray burst, so it's not going to turn you into the Hulk, it's just going to be a burst of highly energetic photons. Now, what we can do is we can use the amount of gamma ray bursts we see, or lack of gamma ray bursts we see, because we don't see too many of them, to put constraints on how many black holes could have evaporated. Then also, as I mentioned, it's related to their mass. So most stellar mass black holes which are the usual ones we're accustomed to, are not going to evaporate for a very, 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 very long time, a couple billions of years at least. So if we see any evaporating black holes today, it could be that these evaporating black holes come from primordial black holes, which would be black holes created in the very early universe. And now let me see some of the questions. Now I know we have a question from Gregorio here. I will come back to that 1 second. Sounds like it might take a while to dissipate an entire black hole. So yeah, like 10 or 20 years maybe, closer to billions of years, Scott. So all of the black holes that we know of would take longer than the age of the universe to evaporate, which is why the universe, to our knowledge, is 13 billion years old. That's 10 to the 9. I know 2 weeks ago I made some mistakes with my units. If I say billion, I mean 10 to the 9, not 10 to the 12. Anytime I say billion, it is 10 to the 9. I know 2 weeks ago I made some mistakes with my units. I always get confused with long scale, short scale. Anytime I say billion, 10 to the 9. Oh, just offhand comment there. So the universe is 13.82 billion years old. That's 13 gigayears, and it would take a lot longer than that for most of the black holes that we know to evaporate. Comment from James, obvious assumption then, can black hole size be measured to a degree that determines as a black hole has shrunk? Now here's the problem, that when we measure the size of a black hole, it's quite a difficult thing to do. But what we normally end up with is something like 5.3 times the mass of the sun, or 30 times the mass of the sun. And you'd have to make this, in order to see a change on the level that we would be able to measure, you'd have to make measurements millions of years apart. If you measure the mass of a black hole every 3 days, you're not going to see a change. You would really need to wait a long time in order for the change to be big enough to actually detect it with the current techniques we have to measure the mass of black hole. Question from David Howden here. The black hole is gaining a particle, one of the pair, so does that mass get added, but a net loss for the energy of the other particle? Yeah, it's fun to think about, right? Because you have the particle and the antiparticle. They both have a certain amount of energy. They both have some type of mass. But it's really that one is escaping and you need to pay back the energy that was used to create them. So even though one particle does fall into the black hole, which has negligible mass compared to the size of the black hole will lose a tiny, tiny, tiny amount of energy, which was the energy needed to create the particles. But it is a very, very, very small amount. You don't see me on Reddit this time. I didn't think I was getting any comments from Reddit. I don't know why. Technically, I should be going automatically to Reddit. I will ask the HAPS team what's happened with that. It could be just a blip in the system, some random issue. I should be going out to Reddit. Not sure why that didn't happen, but you know, it doesn't matter. We just have the HAPS people, the Twitch people, the YouTube people, and the Twitter people. We don't need Reddit, but it is nice when we go out to Reddit as well. At the end of the black hole evaporation, is there an explosion or does the black hole just fade away? Oh, that's a good question. We don't know for sure, but we think there would be, once it reaches some critical threshold, we think there's probably going to be a huge burst of energy, such as a gamma ray burst. Is it really an explosion though? I wouldn't call it an explosion because you don't really have an ignition source. So I'm not sure. I would say we don't know. We do expect that at the end there's going to be this burst of electromagnetic radiation. I'm not sure if that's enough to count it as an explosion. 10 to the 67 years to evaporate one solar mass black hole. That sounds about right. So yeah, it takes a long, long, long time to evaporate a black hole of the mass of the sun. Billions of times more than the age of the universe. Okay, question from Abyss. I see this is already going to be a difficult question. How does the Steinhardt model explain the expansion of the universe? I am not sure. I am not sure about the Steinhardt models. As always, Abyss, you're asking questions that stump me. And as always, I'm going to take a note of that. And it's been a very, very long time since I did anything relating to, where's my screenshot? Why is it not taking a screenshot? There we go. I have a screenshot of your question now, Abyss. It's been a very long time since I reviewed the Steinhardt model, so I can't answer that question. I'm not on HAPS News? Okay, that's fine. We don't need Reddit today. I'll figure out why the Reddit connection failed. I will just ask Peter and Pablo about that later on. Remember watching a video that said black hole the size or mass of a penny in your pocket would still kill you when it evaporated? That is very possible. That is very possible. Yeah, it could be. Sharon was a bit wobbly when I went live yesterday. Okay, that's good to know, David. Thank you. That is good to know. Okay, so now there was a question. Moving on from black holes, we need to force Abyss to phase his questions into Japanese haiku format. Yeah, but then I still won't be able to answer them. But yes, Abyss always has very fun questions. So moving away from the topic of black holes, there was a question by Gregorio that is partially related. Could the energy carried by gravitational wave background considered dark, since it only interacts gravitationally? So this is a very cool question. Now, I guess you're asking whether this energy could count as dark matter. Now, the thing is, one thing that we know about dark matter is that it has to have mass. Not only is it something that interacts gravitationally, but our current models all point to something that has mass. So, if we have radiation, like you can imagine, you can ask the question of, could we have light? So like light, but in the dark sector, so that you have dark photons, for example, dark light. Could this be the dark matter? And the answer is no, because we actually need dark matter to have mass in order to explain the motion of galaxies, clusters of galaxies. Now, again, there are lots of modified alternatives. So there are alternatives to dark matter, such as modified Newtonian dynamics, such as modified gravity, that try to explain what we see and identify as dark matter without invoking dark matter. But none of them can fit the data as well as our dark matter model can. So if we assume that there is something that behaves like dark matter, which seems to be what we need in the universe, it needs to have mass. So even though we can have a gravitational wave background, it cannot account for the effects of dark matter. Now, you also have the question here, could it account for the effects of dark energy? So the thing about dark energy is that we know that it's driving the accelerated expansion of the universe, it's pushing everything outwards. Now, gravitational waves wouldn't do this. They're ripples within the fabric of space-time, but they don't cause an expansion of space-time. So gravitational waves, super fun topic, but what gravitational waves basically do is they vibrate space-time. What dark energy does, on the other hand, is it pushes space-time outwards. So the behavior is very slightly different. Behavior is different enough that we can say that if there is a gravitational wave background, which I really hope there is, it would be amazing if there is, it wouldn't have the same behavior as dark energy or dark matter. So this is one of the few things we know about dark matter and dark energy are its effects on the universe. And we know that a potential background of gravitational waves or any type of relativistic radiation does not behave like either of these two species. It does not affect the universe in the proper way. So that is why we don't think that dark matter is made up of gravitational waves and dark energy is not made up of gravitational waves, just because the way they impact the universe is very different. And I see we have two very, very, very good questions. First of all, I'm going to answer the one by David, and then I will go back to the one by Scott here. So if a gravitational wave hit a black hole, what would happen? I love this question. It's an excellent question. So everything in the universe, as far as we know it, is subject to the curvature of space-time. Space-time curves. This tells objects how to move, and objects with mass are the ones that cause this curvature of space-time. So you have this nice reaction between the two. Gravitational waves are ripples in the fabric of space-time. If a gravitational wave goes through you, it is going to make you grow in one direction and shrink in the other, and then vice versa. So gravitational waves really stretch space-time. So if a gravitational wave goes through a black hole, let me think about this. If a gravitational wave goes through a black hole, it would very, very, very slightly change the size of the black hole in one direction and then in another. Because this is what a gravitational wave does to any object in the universe and to space-time itself. Everything grows in one direction and shrinks in another, and then vice versa. But this effect is tiny. If a gravitational wave, imagine two average-sized black holes, like two black holes of around 10 times the mass of the Sun, smashed together 2 billion years ago, and they produce gravitational waves that travel to us today and go through you. Now, this gravitational wave will make you grow in one direction by 1 billionth the width of a human hair. This is ridiculously small. So now if you think of such a tiny difference on scales of a black hole, it wouldn't be noticeable. So I think it's a really cool question, but basically a gravitational wave would have a tiny impact on a black hole, but it would be such a tiny impact that you would not notice it. It won't really help us gain any knowledge about the black hole itself. I do like your black hole emoji, Paul. That made me laugh a lot. So that is a really cool question, though. I do like to. Another question that people have asked me often is what happens if dark matter interacts with gravitational waves, and it's really cool to think about. Basically, it's always the same story. Gravitational waves will make something grow and shrink. It will expand space and time, but the effect is really tiny. And now there was two excellent questions. First of all, I'll go to Scott and then I'll get to Paul's question because I see Paul is asking something about the CMB. But first, let me get to Scott's excellent question, and I'm going to bring up my standard model of particle physics if I can find my image. Where's my standard model of particle physics? Here it is. Okay, and let me just go back to the comments so I can read the question properly. Very nice question from Scott here. I lost the question. Where's it gone? I jumped to the bottom again. If every particle has an antiparticle, what are antiphotons? This is an excellent question, and before I said everything has an antiparticle, and that is completely wrong. Not everything has an antiparticle. Now what you can see up above you, or that direction, I'm never sure which direction it goes to. Anyway, what you can see in this image that is somewhere around me is the standard model of particle physics. These are the building blocks of all of the known matter in the universe. Everything from the stars to us, to my coffee mug, or my tea mug, all of this is normal matter. And normal matter is made up of these 17 building blocks. So here we have two families, two big families. We have the fermions, which are in purple and green, and we have the bosons, which are in red and yellow. Now the fermions are the ones that make stuff up. They're the building blocks, and the bosons are the ones that tell these building blocks how they fit together, or how they interact. So each boson is responsible for telling the particles how they interact. The graphic is actually above you on my phone. Yeah, if you're in portrait mode, it's up there. If you're in landscape mode, I believe it's over there, but it might also be over there. Depends where you're watching. HAPS does send things around in cool ways. It just makes it harder for me to point at stuff. So, have hair that's annoying me. Yeah, the fermions are the purple and green ones, the 12 blocks you can see on the left, and the bosons are the red and yellow ones. So the fermions are the ones that actually clump together and form structures. The bosons are the ones that tell these how they fit together. Now within the fermions we have two families. We have the quarks and we have the leptons. The quarks can never be found alone. You can never find one up, one charm, one down. They always come together. You either have groups of 2, 3, even 4 and 5 have been found in nature. But you can never find an isolated quark. Quarks always bind together. Whereas leptons can be found isolated. So for an example, a proton, you have up, 2 downs. A neutron, you have two downs, one up. You have these, I always mix those up. So all of these quarks come together. Now, the thing about an antiparticle is something that has opposite charge. So if you have an electron, this is going to be negatively charged, and if you have a positron, which is an electron's antiparticle, it's going to be positively charged. It's to my right, so it should be that way. Thank you. So, in order to have an antiparticle, you need a particle with opposite charge. I'm not sure how well you can see the text here, but you see that each small block has 3 numbers. The top one is the mass approximately, then we have the charge, then we have the spin. Now, if we focus on the charge, you can see that, for an example, an electron has -1. A positron is going to have +1. Now, the problem comes when we look at some of the bosons, particularly when we look at the gluon and the photon. Now, if we look at the numbers for the gluon and the photon, what you'll see is that they have no mass, they're massless, and they have no charge, they're neutral. Now, the thing is, if you have a neutral particle, you cannot have an antiparticle. So most things have an antiparticle. For every up, you could have an anti-up. Now, we know that there are a lot of ups in the universe. There's not many anti-ups, fortunately. You can have an anti-charm, you can have an anti-top, you can have an anti-electron, which is a positron, you can have an anti-muon, an anti-neutrino. Sorry, not an anti-neutrino. because neutrinos also have charge 0. So you can have a lot of antiparticles, but not all of them. If they have charge 0, they do not have an antiparticle. So this was a great question, Scott, because you asked what is the antiparticle of a photon. Photons do not have antiparticles because they do not have charge. So photons do not have antiparticles, gluons do not have antiparticles. We think there's no anti-Higgs either. So the top 30% is cut off on the phone. Yeah, I honestly don't know why HAPS haven't fixed that yet. I guess it's a difficult bug to track down, but it is quite annoying that things are cut off depending on the phone. Scott, if you could send me the details of your phone, like which device you're on and which operating system, I will file a bug report and see if we can fix the fact that things are getting cut off. So, yeah, it's an excellent question. Are there any antiphotons? The answer is no, there are no antiphotons. Neutrinos could potentially be their own antiparticle. That's still up for debate, whether you can have antineutrinos and what that means. But currently, we don't really deal with that so much because it's a fun topic. But it gets a bit messy when we move to neutrinos. But to answer the question, there are no antiphotons because photons do not have charge. So that was what I wanted to say about that. And I know I missed some comments here, and there was still a CMB question I need to get back to. And before I do that, I really needed to get a drink. I saw someone in the comments just now mentioning Quizgazakt, and of course I have my Quizgazakt mug with me, because I don't yet have a mug with my own logo on it, so I'm using other people's logos for now. But I do need to get a mug with my own logo on it. Question from David, follow up to what I was saying. If I had some quarks bound together and pushed them just over an event horizon so only one stayed outside, could I then get one on its own? So the cool thing about quarks is that it is really, really, really difficult to separate them. They are held together by the strong force, and as the name implies, the strong force is very strong. Very, very, very strong. If you have two quarks that are held together and you try to pull them apart, like you have one quark, you have two quarks or held together in a meson. Meson just means two quarks. You pull them apart. The energy you need to pull them apart is actually enough energy that you could create more particles. So if you try to pull two quarks apart, what you're going to end up with is two quarks here and two quarks here. Because the energy you're putting into the system to pull these apart is enough to create more quarks. So you cannot pull them apart. So if you have quarks bound together and you push them just over the event horizon, the strong force is stronger than gravity. So I think even in a black hole where you have the strongest gravitational force possible, it should not be strong enough to rip apart the quarks, I think. But then it's a fun thing that we don't know what happens inside the event horizon. But if you were to hold a particle just like half in the black hole, half out, I think it would all go in just because the binding energy of the quarks is really strong. But this is a super cool question, David. I really like this question. This is actually really cool. But I would say the quarks would stay together just because the binding energy of the strong force is so strong that you can't pull them apart. Okay, thanks, Scott. I just saw. I will ping you, Scott, to ask you more details about the phone so I can file the bug report. Okay, more questions about the standard model. I have not forgotten. There's a CMB question I haven't answered. Foundational question, how much of the standard model was established with collider tests and how much outside, if any? So the cool thing about the standard model is a lot of it is predicted theoretically. A lot of it is most of the standard model, in fact all of the standard model for now has been stuff that we've predicted and then found. Is that true? Yes. I think there was one particle that we found before predicting it, and no. All should make perfect sense. A lot of this has been found in colliders, but not everything. Some of it has been found by other means, like neutrinos. We didn't need colliders to find neutrinos. But colliders such as the Large Hadron Collider, where you smash particles together at high energy, gave us the Higgs boson, which was the missing piece that completed the standard model of particle physics. So, yeah, it's a lot of it has been thanks to colliders, but not everything. But colliders have also helped us find things like tetraquarks and pentaquarks, which are combinations of 4 quarks. So we're used to mesons, which is 2 quarks, and baryons, which is 3 quarks. But colliders, like the Large Hadron Collider, have also found tetraquark, which is a combination of 4 quarks, and pentaquark, which is a combination of 5 quarks. So that's pretty cool. I know other people pronounce it quark. It's a matter of debate. Both are acceptable. Okay, and now going back to the CMB question, because I cannot ignore a CMB question this long. Question from Paul. Do different parts of the CMB have motion relative to other parts? Since the CMB is early light, I think I am asking whether the things that emitted the CMB were moving relative to each other at the time. This is a great question, Paul. This is a really, really nice question. And you know what I have to do, because I'm talking about the CMB, and I can't talk about the CMB without showing the CMB. I don't actually need the image, I just want the image. CMB. Okay, quick recap for anyone who is not familiar with the CMB. The CMB is the cosmic microwave background radiation. It is the oldest light in the universe that we can see in any direction we look. You can tell I get carried away. It is the afterglow of the Big Bang. This is really the picture of what the baby universe looked like. And what you're seeing here are particles of light, these photons, that were produced in the very, very early universe. In the very early universe, you had three main components. You had dark matter doing its own thing. It's not invited to this story yet. But you had three main things. You had photons, you had protons, and you had electrons. Now, as the universe cooled down, the protons and the electrons could combine together to form hydrogen, and the photons could no longer bump into the other two species. At that point, the photons broke away and they started traveling freely in the universe. They've been traveling freely ever since. Now, the cool thing is that this happens everywhere in the universe at the same time. This is why, from our point of view, the CMB is a sphere around us in every direction we look, the same distance. So the CMB is about 43 billion light years away from us in every direction we look. And it really is the idea here is that these photons decouple from everywhere in the universe at the same time. Now, as you are asking here, like, could there be motion? There were for sure some things moving at this time, but everything decoupled at the same time. So when we look out at the CMB, what we're seeing is the particles that are coming towards us from this time of decoupling. Now, this time of decoupling is often referred to as the last scattering surface, which is the last surface on which the photons could scatter or bump into the protons and the electrons. Now, because they broke away from this last scattering surface at the same time, this last scattering surface is the same distance away from us in every direction we look. So back to your question here, I think I partially answered it. Do different parts of the CMB have motion relative to other parts? The answer there would be no, because they are all the same distance from us, and the light traveling towards us travels at the speed of light. So because we're at the center of our own observable universe, the CMB is a sphere located around us. So there's no motion within the CMB relative to other parts of the CMB. However, there is an overall motion of the CMB from our point of view. The reason for that being that we are moving around our galaxy. We are traveling around the Milky Way, and because of this, from our perspective, the CMB is slightly shifted. We have this overall motion of the CMB from our perspective, which is caused by us rotating in the Milky Way. So when we look at the CMB, what we actually do is, to get this image that you see up here or in one of those two directions, what we do is we subtract away the motion of the Milky Way relative to the CMB. So the CMB itself is not moving relative to other points, other than, traveling towards us, but we are moving relative to the CMB. So we correct for our own motion in order to get this map without the motion that we're adding here. I hope that answers your question. Do let me know if that doesn't. And thank you for giving me a chance to talk about the CMB. As always, I love the CMB. Okay, going back through the questions, I see there were comments in Japanese. Please do not ask me to read the Japanese kanji. I'm not yet there. Okay, going back through the questions. Do you say CMB? Yes. I think I covered all of these questions. Let's see, we've done the quark one at the black hole. Excellent question there. Going through, just checking that I didn't miss any questions there. We did the foundational question about colliders. Comment from Abyss, you remember you asked about black holes and gravitational wave interactions right after LIGO confirmed black hole collision in 2017. Well, it was 2016 actually. The first confirmation of gravitational waves by LIGO was in 2016, February 2016. It has been 6 years now since we got the first real measurement of gravitational rays coming from black holes smashing together is really cool. Time does indeed fly. It's been 6 years. Just a reminder that this stream, this Cup of Cosmology, has now been going on for 6.5 years, and you're all still here. Some of you I've known for 6.5 years now, every weekend coming to watch me live, and sometimes even during the week. And I love that you're all still here, still coming back after 6.5 years, and that I still have fun things to talk about. And yeah, great to be here, great to have everyone here. Comment from Scott, my logo is a mug, so a mug of your logo would be a mugception. It would indeed, but I do need to get my logo on a mug because it's an awesome logo. I'm not sure what James was saying that's incredible to, because I'm a bit delayed with the comments, but I agree. Everything I've talked about today is incredible. I'm not sure what the comment was referring to, but I'll take it. Just going through, making sure I've caught up with all the comments. I do indeed love showing off the CMB. The image always gets me excited. Is the CMB the same in Australia? It is indeed. There's actually a cool thing that a cool exercise that we set the undergrad students when I was TAing or tutoring general relativity. There was a cool question we set the students. I hope they think it was cool. I thought it was very cool. Once we did introduce, no, it was actually in the Perturbed Universe lecture, so Advanced Cosmology. Once we'd introduced the CMB and built it up, we asked the question of like, how long would you have to wait in order to see a completely different CMB? And the question can also be phrased as like, how far away would you have to travel in the universe in order to see a completely different CMB? It's really cool. I hope the students found it cool. We said it as an exam question at some point, and I was partially responsible for that being an exam question, but it's a fun question, and you can calculate it. And yeah, the answer was about 10,000 years. 10,000 or 100,000? I need to redo the exercise. 10,000 years you need to wait in order to see a completely different CMB to what we see today. So that's pretty cool. We need to have a Mercantile projection map of the CMB. We do indeed. You know, you can actually get spheres with the CMB printed on it. And I do not have one yet, and I really need to get one. You can get like a beach ball of the CMB. Incidentally, there is one hanging up in the seminar room in my office building. So I walk past it the times I actually go to the office, and every time I'm reminded I can need one of those. So I do need a CMB, but you can actually get spheres of the CMB. I know there was a conference at some point, one of the early, I believe it was early Planck conferences, where everyone got a ball with a CMB on it, and I want one. How different is different? The temperature shouldn't change so much in 10,000 years. So the temperature itself doesn't change so much, but the idea is you get different statistical distribution. Was it 10,000 or 100,000? I need to redo the exercise, but the point is if you wait long enough, you will see a different CMB map to what we see today. We were counting different at the level of once you take the angular power spectrum, which is basically the fingerprint of the CMB, at that point, you can have a noticeable difference. Yeah, it's not the CMB itself that changes, but the fluctuations. So these tiny temperature changes that we have in the CMB. But yeah, we definitely need more CMB projections. If I sell those CMB beach balls, all my customers will have to come back in 10,000 years. Yeah, it's a good business model. And you know, you could do the one currently, the CMB with our current understanding from Planck, and then update it as we get more and more precise measurements of the CMB. You think it was 10,000, you remember from the TTK scopes? Yeah, because we did a TTK scope at the time when I was teaching that or when I was TAing or tutoring that. So yeah, it is true actually that I've used this example so many times going back years. Some of you have good memory from the TTK days. Hey Molly, great to see you. I remember you from HAPS. It's nice to see you now on Twitch. Welcome back. Great to have you here. Great to see you again. Thank you for being here. So yeah, it's been a while. I will try to get some of the TTK members back on for like another reunion. We did one last year for Dark Matter Day. I'm going to try to get more of the TTK members back online. I have a few people in mind. Now that I think about it, next week I will probably have a guest online. Still need to be 100% confirmed, but I should have a guest next week from my current office, which will be nice. So we've already covered the topic a bit today, but now I have a question for everybody watching. In 2 weeks, less than 2 weeks, Friday the 18th, I believe, let me check my calendar because I'm bad with dates. Friday the 18th, I am giving a public outreach talk with slides and everything about gravitational waves. It will be for the iTelescope network. I will send out the link when you can register. It will be completely free. I gave a talk for the iTelescope network early January on the topic of dark matter, dark energy. It was super cool. We had about 300 people join and a bunch of questions. I think I gave a 1 hour talk and then 1 hour Q&A. It was super fun. So on the 18th, Friday 18th, I'm giving a talk about gravitational waves. So now I have a question for everyone here. If you were going to attend a talk about gravitational waves, which you're going to because I assume you're all going to come to my talk, what topics would you like to hear me cover? Because there's a lot one can talk about gravitational waves. So let me know here in the comments, wherever you're watching from, what topics should I discuss if I'm discussing gravitational waves? Because I have a very, very, very long list, and I don't think I can fit everything in 1 hour. So when is this? March the 18th. It is indeed March the 18th. And I can confirm the time. It should be at the same time that my streams are. So that's 8 p.m. Helsinki time, 7 p.m. European time. That should be 1 p.m. Eastern Standard Time and 10 a.m. Pacific Coast, West Coast. The fact that I'm able to do that in my mind now, I'm still happy about that. So yeah, that should be 18th, same time that my streams are usually, but on a Friday. I will tweet out the registration link once it's open, but I think you can already, I'm not sure if you can already sign up, but it is already advertised on the iTelescope webpage. And you should all check that out because already this Friday there's a talk, and the week after me there's another talk by people that I know. One's on quantum gravity, I believe, or on the quantum world. One's going to be on supermassive black holes. They're both going to be really cool. They're both by great speakers, so do check out the iTelescope talks. It will be weird to see me talk and not be able to distract me with weird questions. The weird questions are some of the fun things, right? But there will be plenty of time for questions just at the end. But it also means you'll get to see slides. And I like making slides. I put a lot of cool stuff in the slides usually. And I obsess over the color scheme and the formatting. Definitely don't spend too long on my slides. So it will be a bit more formal than the presentations here, but then I can actually show some equations and some math and go into a bit more detail. So do check it out if you want to know more about gravitational waves. Ground-based versus space-based gravitational wave detectors, awesome, Paul. That's a topic I definitely plan on discussing. Do you already change your clocks? Oh, shit. Then maybe it's not. Maybe I've got the time zone wrong because if you people change your clocks, I know in America you change your clocks differently to the rest of the world because US always does things differently. I think, okay, I need to check because I might have the time zone wrong. Thank you for that comment, David. I might have missed my own talk because of the time zones. If you people change your clocks beforehand, then I need to check that. Okay, what are gravitational waves? What are they waves in? How are they made? Then on to studying them. Okay, awesome. And how they will let us know about the universe. Perfect. Definitely topics I can discuss. The procedures in capturing them and how that compares with capturing other things. Oh, that is a great one, James. That will also be in the talk. I think the detection of gravitational waves, like how interferometers work and how the sizes of colliding black holes or neutron stars can be predicted. Nice. I don't actually think I usually cover that. Yep, I can add that in a bit because that is also really cool, of like how we actually know the size of the black holes. Okay, lots of topics. This is the problem. There is so much to talk about gravitational waves, but thank you all for the pointers and letting me know what you want to hear about, because then I can cater the talk to fit. Yeah, it's about 45 minutes to 1 hour. Last time I was told around 45 minutes. I went for an hour. Everyone's happy with that. And then we did a whole hour of Q&A. So the talk should be 1 hour. Okay, so the US changes clocks on March the 13th. Okay, I do believe the talk was agreed in UTC. I need to check. But it will either be, sometime between, like, the time I quoted plus minus 1 hour. I will confirm on Twitter. And I will confirm next week's stream as well, because this is still 12 days away, so there will be one more stream in between. So I will confirm the times next week as well. But thank you for pointing that out to me, because now I need to check the time zones. Just when you think you figured out time zones, they throw at you summertime. Daylight saving time. Daylight saving time makes no sense, by the way. There is no scientific reason to keep this changing of the clocks in summer and winter. It makes no sense. It should be abolished, and this is a hill I'm willing to die on, because it's ridiculous. And I have a very good internal body clock. I'm very good at waking up exactly 2 minutes before my alarm every day. And then when we suddenly change the clocks and my sleep schedule is messed up, it takes me a week to adapt. I spend a week not sleeping properly, and it's pointless. It makes no sense. I know I've just gone on a completely tangential rant here. We need to get rid of daylight saving time. It makes no sense. And we need to keep to winter time. Some people are like, let's stay to summertime. No, we should keep to the winter time. Anyway, as a bit of saying, an hour off from my insomniac sleep schedule, right? It makes no sense. We should not be doing it, and not all countries do it, which makes it even more confusing. It makes no sense. This is something that I will always have energy to rant about, because it makes no sense. Get rid of all time zones and make Earth one time. Now that would be confusing for everyone, because then setting things up would be easier, but it would just make things so confusing for everyone. I think, that's what we have UTC for. All time should be given in UTC, and then everyone can just figure out how many hours plus minus UTC you are. Because UTC is exactly universal time, so it's the one to use. It's the one they use on the International Space Station. It's the one that we should use for everything. But it doesn't work like that. Okay, so I think I've gone through all of the questions. Please do keep them coming. I know without the Reddit people there's fewer questions than usual, but you've all had great questions so far, and I'm still on for another 12 minutes or about that. So you can still ask any questions you have. Anything you want to know about space, time, the universe, everything inside, about Doctor Who, seeing as I have a poster behind me. Anything you want to know, feel free to ask. I will try to answer your questions. Changing the clocks is stupid, yes. And if you are doing a wildlife survey, it's annoying to note the length of it at the start-finish times don't difference. Yeah, I feel you, David. It makes no sense. It's just, it messes up so many things. There's just no logical reason for it. China has one time zone, though it literally should have 3. Right. I've actually never realised that, but you're right. You're right. China only has one time zone. Curious. And then you have countries like Spain that are on the wrong time zone. Spain should be on the same time zone the UK is on, but Franco, the dictator, wanted to be on the same time zone as the rest of mainland Europe, so he changed it. But Spain is actually on the wrong time zone. Based on its geographic location, Spain should be in the same time zone as the UK, and it is not. What about that black hole that's tilted on its size? On its side? I'm not sure, David. I'm not sure what you're referring to. There is, I haven't been reading space news in the last week. I saw there was something about a new black hole, but I haven't actually read up about it just yet. But I will. I've been a bit behind with a lot of things lately. Work's been piling up. I've been working way too much. I need to stop doing that. And I've been thinking about grant proposals, which is a good way to stress yourself, and I do not recommend grant proposals, but they need to be done. So I'm a bit behind on my science news, actually, which is why I didn't have a topic prepared today, because I didn't read the science news. So if all goes to plan, next week I should have a guest on from my institute who works on similar things to what Anna worked on, who was on the show 4 weeks ago. And we will talk more about how we simulate things in the early universe, so how we actually study the early universe and what we can do to understand the universe. Because the problem that we have about the universe is that we can't put it in a box. We can't put it in a lab to run experiments on it, right? And we can't build our own universe in a lab in order to run experiments. So there's always a question of how do we study the universe? And one way we can go about studying the universe is by simulating the universe. Simulating the universe means you tell the computer, here's everything I understand about the universe, show me what the universe should look like. And this is really fun because these simulations are not easy to do, but they're the backbone of a lot of what we do in cosmology these days. And there's a lot of different types of simulation. Some people will simulate how galaxies form. Some people will simulate how matter interacts within the universe. Some people will simulate how the early universe behaved. Some people simulate things like gravitational waves and phase transitions in the early universe. And all of these require different codes, different techniques, different approaches, and it's super fun. The good thing is, once you know how to simulate something, it's easy to move on to other simulations. In principle, in practice, it's not so easy. But simulating stuff is fun. So next week we will probably, I still need to confirm, but next week we will probably talk about some things in that direction. Comment from James, thank you. I know I'm just rambling at this point. Strangely fascinated with gravity associated with size or density. Could a human live in a rocky planet the size of Saturn if it was Saturn's density? Now, the thing is, Saturn is a very, very, very light planet. In fact, Saturn is so light that if you put Saturn in an ocean, hypothetically, of course, because you cannot put Saturn in an ocean, but if you were to put Saturn in an ocean, it would actually float. So Saturn is extremely not dense. It is very light. And that means that it doesn't have the density in order to form a rocky planet. In fact, one of the main differences between rocky planets and gas giants is their density. So if you want to have a rocky planet with the density of Saturn, you already have an issue there. Could a human live on a rocky planet? Well, obviously, assuming it's habitable and so on. The size of Saturn, but with Saturn's density. See, that's what I'm not sure about. If somehow you could make a rocky planet that had the density of Saturn, which would be very, very difficult, then you'd have to consider what the gravitational pull would be on the surface. I don't think humans could survive on Mars, on the Moon, if we specifically modify the habitat. I'm not really sure. I know you can, but I think the lack of density on Saturn would make it very difficult to do anything. But if you have enough things kind of weighing you down, then you're not going to float off, so that's okay. So I think it's a curious question there. So Saturn is very much not a dense planet. That's why Saturn won the swimming competition in my Planet Olympics last year. Last year we did a Planet Olympics. It was super fun. It would probably be a spongy planet. Yes, spongy planet would be fun. Oh, how would we detect a Dyson sphere? I do want random questions, David. Thank you. I love Dyson spheres. So Dyson spheres are kind of an idea that an advanced civilization could try to harness all of the power of its own star. And one way you could do this is with a Dyson sphere. So a Dyson sphere would be a sort of swarm of satellites, rockets, structures around the star that would harness all of its energy. Not all of it, but which would it would absorb I just got distracted by the comments. It would kind of be like a super solar panel that would absorb the energy of the sun and charge and produce unlimited power. And it is considered a staple of advanced civilizations. Depending how advanced your civilization is, at some point, in order to progress, you need more energy. This is a problem we have here on Earth. we don't have enough energy. Oh, I've lost my voice. So we do have an energy crisis. We don't have enough energy. We are still ridiculously dependent on fossil fuels, which we should move away from. We should have moved away from them 50 years ago. We absolutely need to move away from fossil fuels as soon as possible. For the benefit of the whole of humanity, we need to move away from fossil fuels. But we do have this problem that we're lacking energy. In order to progress as a civilization, what you need is more energy. One futuristic idea in order to have more energy is a Dyson sphere. So this would be just a structure around the star harnessing as much energy in order to advance a civilization. It's something that currently we wouldn't have the technology to build it today, but it's something that is super, super useful, super interesting. And there are excellent Quizgesagt videos about Dyson spheres. So Quizgesagt is my second favourite YouTube channel, other than my own, of course. It's a great YouTube channel. I really recommend checking out Quizgesagt. It's absolutely best YouTube channel, really cool animations, really cool science outreach, a lot of information. You can spend hours just watching random quiz exact videos and you'll learn something in every single one of them. And they have great videos and posters and a lot of information about Dyson spheres. So how would we detect this Dyson sphere? Now the cool thing is, one way that we have of detecting exoplanets, or in general stuff floating around stars, is to look at the light coming from a star. Now if you look at the light coming from a distant star, and at some point you see this light getting dimmer, then you say, okay, maybe something flew in front of the star. Now if this happens every 100 days, for an example, you might say there is something orbiting this star that every 100 days passes in front of it from my line of sight and causes the star to lose a tiny, tiny, tiny bit of energy. Sorry, tiny bit of luminosity, not energy. From where we're looking at it, the light diminishes in intensity very slightly. So this happens every 10 days, 100 days, and you say there's something orbiting around the star. This is what we call the transit method. Now, if there's a Dyson sphere, depending on how the sphere is orbiting around the star, there could be times where you see more light or less light coming from the star. Now, of course, if there's like a constant swarm going around and it doesn't change the light of the star in any way, then you have an issue. But it might not be aligned to the way you're looking, and there might be some things of how the Dyson sphere is moving that could help us detect it using the transit method. So one way we would have of detecting a Dyson sphere, and I love this question, David, one way you would have of detecting a Dyson sphere is just looking at the intensity of light coming from the star and seeing if there are any changes. And now this brings me to Tabby star. And I'm going to start by saying it is not aliens. And of course, David, you got to Tabby star at the same time I did. Now, Tabby star is a star that we've observed that had a weird pattern where the light diminished, almost as if a swarm of something had passed in front of it. Now, there's a lot of things that could explain this. And this is one of those times where a scientist made a flippant comment that was blown out of proportion and it became a big thing. And someone made a comment of, there's a lot of things that could explain this swarm. We can't rule out, for an example, an alien megastructure. As in, there's a 1,000 possibilities and one of them could be an alien megastructure. And the scientists made this flippant comment like, we can't rule out it being an alien megastructure. And of course, the popular science news articles printed it as, does Tabby star have an alien megastructure? Probably not. Probably not. It was most likely a comet that disintegrated and passed in front of Tabby star. But Tabby star is now associated with the star that had an alien megastructure. Probably not. It seems much more likely that it was a comet that smashed up into something. The comet smashed in something, created a lot of debris, and this is what we saw. So some people were saying this looked like it could be a Dyson sphere around Tabby star. It was very unlikely. It is very, very, very much not likely to be an alien megastructure. You know, if in doubt, the safest course of action is to always assume it's not aliens, because that is the most likely scenario. It is never aliens until it is. And you know, the day it's aliens, we will all open with, so, it's aliens. Until we do that, ignore what you read in popular science news about have we found aliens. The answer is always no, it is not aliens. You know, it's aliens? No, it's never, never aliens. But was it a swarm of giant space bees? We can also not rule out a swarm of giant space bees. It could be a swarm of giant space bees in the same way it could be an alien megastructure, meaning it's unlikely to be either of those two things. So what is a Dyson sphere? A Dyson sphere is a sphere or a megastructure, a constellation of satellites that orbit around a star and absorb its energy and distribute it to the civilization. So you can imagine if we were equipped to do this in the future, what we would do is we'd build this alien structure, this mega structure around the sun, and we would use it as a highly receptive solar panel that has excellent storage capacity and could not only store the energy but could then distribute it. One potential thing is you could have a swarm kind of like this structure that has the solar panels, highly efficient solar panels, and I'm brainstorming here because we don't know how to build a Dyson Sphere yet. And then you could have other baby satellites that collect the charged batteries and distribute them throughout the solar system. So a Dyson Sphere is basically a way of harnessing the energy of a star, and it's something that is considered necessary in order to have interstellar travel. In order to travel beyond the solar system, we need more energy. One way of obtaining more energy, because the sun, our stars, have a lot of energy. So the most logical thing to do is to harness as much power from the sun as possible. One way to do this would be a Dyson Sphere. Hope that answers the question of what is a Dyson Sphere and how should we detect it. And thank you for bringing up that topic because it's really fun. I like talking about Dyson Spheres, and I don't get many chances to talk about Dyson Spheres because it's not a usual topic on my streams. But I do like Dyson Spheres. And we've reached the 1 hour mark. Thank you everyone for all the really cool questions. Not aliens. Yeah, I do work for the Men in Black, you know. I do look good in a suit, but yeah. Anyway, comment aside, it originally needs to be preserved. We should rename Dyson Spheres to Stapleton Spheres, yes. Difficult things to build. If we figure out how to build a Dyson Sphere, that would be cool. But before we can get to a Dyson Sphere, we really should be moving away from fossil fuels. We have hundreds of reasons to move away from fossil fuels here on Earth, the biggest one being climate change, which is going to have huge impacts. But anyway, let's end on a high note and not about the climate catastrophe that is coming to us unless we do something now to prevent it. We are almost too late. But let's not focus on that just now. So thank you everyone for the questions. It's been great fun. I did not have a topic prepared today, and I'm very happy that you all had enough questions to keep this going for the whole hour, because sometimes I don't have time to prepare topics, and it's nice to know that when I don't have time to prepare topics, you still have enough questions that we can make this work. So thank you everyone. It's been super fun. I will be online again next Sunday, same time as always. If you change your clocks, check the time zone. I will always be online at 8 p.m. Helsinki time. So check your time zones. On my webpage, there's always a time zone converter. So if you want to figure out what time I'm on in your own time zone, just go to my webpage. That's cupofcosmology.com. Cupofcosmology.com. Go there. You can click on my time zone converter and figure out what time I'm live in your own time zone. And that's probably the easiest way to do it when we all start changing clocks back and forth. So thank you, Abyss. Thank you, everyone else, for being here. It's been great to see you. I'll be online again next Sunday, potentially with a guest. In any case, I will still be here. If you have any questions, you can send me messages on Twitter, or you can also reach out to me using contact@cupofcosmology.com. I'm always happy to receive emails. Anything you want to email me about, feel free. It's always nice to hear from everyone watching here. So, you know, if you have a random thought about the universe, feel free to send me an email. I'm always happy to listen. So thank you, everyone. This has been great fun. I hope to see you again next Sunday. And I hope in the meantime, everyone stays safe and take care of each other.